This is problem 51 from electric circuits. Imagine an n-turn loop of radius capital R. When the loop carries a current I, calculate the magnetic energy stored in the device. In part A, we're assuming the magnetic field is uniform and equal to the value of the field at the center of the loop, and we're going to calculate the inductance of this n-turn loop. So, assuming the field is uniform and equal to the value of the field at the center of the loop. At the center of the loop here, you may remember the magnetic field would be equal to mu naught I divided by 2R for just one loop, mu naught I divided by 2R, but this is an n-turn loop, so I have to remember to multiply by n. Calculate the inductance of this n-turn loop. So that's the magnetic field. And if you go back to page 6, this is what we talked about at the very beginning of this section. We have the inductor, where the inductance is equal to the flux divided by the current I. That is on page 6 here. We're also going to need the expression at the bottom of page 6 for the amount of energy that's stored in the inductor, because they asked us to calculate the magnetic energy which is stored in the device. Actually, even though they asked us to do that, I don't actually think that's one of the questions that's asked beneath. But anyhow, assuming the magnetic field is uniform, so I also need the inductance is equal to the flux divided by the current. So, in order to calculate the magnetic flux, remember from the induction section, the flux is equal to B dotted with A. B is equal to N times mu naught I divided by 2R, and A is the area of the loop, which would be N times pi R squared. And so I have n squared times pi times mu naught I. One of these r's cancels out, and then I have a 2 in the denominator. Then for the inductance, I just take this flux and divide it by I. So the inductance would be n squared times pi times mu naught times r divided by 2. So there is my inductance. And then in part B, it asks how much current must flow in a 2,000 turn loop of radius 10 centimeters in order to store 5 joules of magnetic energy. So now I'm going to use the expression here for the energy that's stored. And so I'll just rewrite that. And then I want to store 5 joules of magnetic energy. And n is equal to 2,000, so I'm going to use this equation here with n equal to 2,000. And r is equal to 10 centimeters. So that's my inductance. This is times I squared, right? So then I just solve for I. And you can do that on your own, and we should get I is equal to 3.55 amps. So you can check to make sure that that is correct for problem 51.